Okay, so for part one of homework 7-1 here, we'll pick up with a few multiple choice questions. So for the first question, they're asking is the sum of the external torques, if the sum of the external torques is zero, then the sum of the external forces must also be zero. Is that true or false? And so don't be thrown off by this one, right? We can have a lot of situations where the external torque might be zero, but the sum of forces would not be zero. So an easy case of that would be maybe if I have a pivot point right here, right? If I have a pivot point, and then if I have two forces that act maybe this way and this way, right? Those two forces would generate a torque, or would generate two torques that potentially balance each other out, but the net force would clearly be going in the upward direction. So we can definitely have a situation where the torque is zero, but the sum of external forces is not zero. So that is false. That does not have to be true. And that's one of the biggest concepts to be comfortable with this. Just because the net torque equals zero does not mean the net force equals zero, and vice versa. Just because the net force equals zero does not mean that the net torque is zero. So those two really are in a lot of ways independent of each other because the radius comes into play and because the direction comes into play. So don't be thrown off by question one. Question two gives us 5 different scenarios here and asks which one applies the greatest amount of torque based on the pivot point P. So we can see P is located on the left-hand end of each of these. Right, so which of the 5 would depict the greatest amount of torque? Well, the biggest torque is going to come from when the force is as far away as possible. So that helps me rule out 2, right? So the force does need to be acting at the far end of that. And then I want the force to be as perpendicular to the board as possible. So in diagram 1 here, the entire force is perpendicular, and therefore that's going to produce the highest amount of torque, right? Diagram 3 over here, you'd have a pretty close to the same amount of torque, but there is a component that goes perpendicular and a component that goes parallel. So some of that force would be wasted going parallel to the door and not generating any torque. 4 obviously exaggerates that situation even more. Only some of that is perpendicular, only some of that is horizontal. And then finally 5 wouldn't do anything in the way of torque, because if we exert our force directly into the axis of rotation, we don't produce any torque. So anyway, again, question 2, probably a pretty easy one for us to get through. Okay, so question 3 tells us that there are 2 correct choices, so which of the following will be true? We've got point P, which is midway between the center, and we've got point Q, which is on the rim of the rotating object. Right, so it does tell us it moves with a constant angular velocity, and again, they're asking us to identify 2 of these that are true. So P and Q have the same linear acceleration. Well, that's not true. The linear acceleration would depend on both the tangential and the centripetal acceleration, and each of those measurements is going to depend on r. So we know that they're going to have the same angular acceleration, but since they have different radius, they're going to have a different linear acceleration resulting from them. So that one's definitely not true. Option B, however, is true. Q is moving twice as fast as point P. Again, if I think in terms of velocity, if I'm thinking linear velocity, the linear velocity equals the radius times the angular velocity. So if they have the same angular velocity but Q is twice as far away, then it's going to be moving twice as fast as point P. And then option C is the other correct option here, and that has to do with linear acceleration. So we have 2 forms of linear acceleration. We have tangential acceleration, which is r times alpha, and we have centripetal acceleration, which is v squared over r, or if you represent this in terms of angular measurements, this would be r squared omega squared over r, so it would be r times omega squared, right? So those are my 2 forms of linear acceleration. Well, if the disk is moving with constant angular velocity, then its angular acceleration is going to be 0. So it doesn't have any tangential acceleration. So its only form of linear acceleration, right, because normally both of these would be linear, but in this case its only form of linear acceleration is centripetal. And since the radius to point Q again is twice as much, but they have the same angular velocity, then point Q is going to have twice as great of an a linear acceleration as point P. So option C is the other correct option there for us. Okay, so obviously then D I can rule out. P is not twice as great as Q. And then the angular velocity, well, the angular velocity they told us is the same, so obviously E is not the correct choice. So question 3, probably a little bit trickier. The biggest part to pay attention to is what does it mean to be linear acceleration? Again, linear acceleration truly means both tangential and centripetal, but since we have a constant angular velocity, the tangential acceleration is 0, so I only have to look at what happens to the centripetal acceleration. Question 4 is hopefully a pretty quick concept question, right? So a rigid body rotates about a fixed axis. All the points have the same. And again, the key here is they will have the same angular measurements. If it's a rigid body rotating around a fixed axis, they will all rotate at the same rate. So any type of angular measurement is going to be the same. Tangential speed, however, would not be the same depending on how far away it is. That is not the same. So again, angular acceleration is going to be my correct option. Again, tangential acceleration has to do with the radius, so that doesn't work out to be the same for every point. Linear displacement, my delta x, would obviously depend on the circumference that it's traveling through. And then the centripetal acceleration, as we just saw in that last question, even if you're relating it to the angular velocity, it still depends on the radius of the particle. And so each of these four depends on the radius, which means the angular acceleration is the only one that's the same for every point on a fixed or on a rigid body as it rotates. Okay, so question 5 obviously involves several steps, but I hope you guys agree that it's not actually too bad. I did go ahead and write the answers, so if you want to just double check those answers, if you're confident, obviously feel free to jump ahead in the video. But I'll work this out entirely for those of you that feel like you might need it. Part A, hopefully part A is not too bad. So they tell us the wheel has been accelerated for 10 seconds. It reaches its top angular speed of 96 radians per second. Then it runs at a constant speed for 40 seconds before it's shut off. As it's shut off, it then slows down uniformly at this acceleration until it stops. So for part A, they ask how long after the time the power shut off does it take the wheel to stop. So the key there is, if I think in terms of kinematics, my initial angular velocity as it's stopping would be that highest speed, right? That 96 radians per second. My angular acceleration would be a negative 1.5 radians per second squared. So as it's slowing down, that is a negative number. And then my final velocity, I know it would reach 0 because it stops, right? So I know it comes to rest. So from these three pieces of kinematics, I can really find whatever else I may want, right? So in this case for part A, they're asking me to find the time. So if I'm doing that, I'm probably just going to use my final angular velocity equals my initial plus alpha times t, or WOTAT if you prefer, right? But anyway, I've got those measurements to plug in. So 0 equals 96 minus 1.5 t, and then again solving for t. So that's where I just take, I obviously add this over the other side, divide by 1.5, and I get 64 seconds. So it takes 64 seconds then for this machine to slow down from that highest velocity until it reaches rest. So then for part B, and part B, again, really not anything too difficult. The only tough part is there's really kind of 3 stages in motion. They ask us how many revolutions was the total number of revolutions made by the machine from the time it's turned on until the time it stops. So there's really 3 stages in motion we're going to have to find here, right? There's a period of time where it's accelerating. So there's a period of time where it's picking up speed, right? So it's picking up speed. There's a period of time where it's traveling at a constant velocity, so moving at a constant velocity, and then there's a period of time where it is slowing down, right? So it's slowing down until it comes to rest. We need to find the theta for each of those. We need to find the number of radians or revolutions for each of those measurements. Okay, so that's all we're going to do is we're going to find those separate measurements. So to find out how fast or how many, revolutions it makes as it's picking up speed, right? Probably the way that I want to do this is the initial velocity times time plus 1/2 at squared. So the only problem there is right now I don't know the initial acceleration, right? They tell me though that it starts at rest, it takes 10 seconds, and it reaches a final velocity. So I can use the final angular velocity, and I can use that to help me find the acceleration first, right? So if I use this equation again, I know it reaches 96 radians per second. I know the initial velocity is 0. I'm looking for alpha, and I know it took 10 seconds to do it. So obviously then alpha would be 9.6 radians per second squared. So now I have alpha. I can use that over here for my my theta equation, right? For my position function, if you will. So I've got delta theta equals, again, the initial velocity of 0 times 10 plus 1/2. It is a positive acceleration as it's picking up speed, and then times 10 squared. So half of 9.6 would be 4.8. That times 10 squared, so that times 100, and I get 480. So delta theta equals 480 radians. And keep in mind, this is the number of radians and not revolutions. But I'm going to go ahead and find all of my measurements in radians and then just convert them at the end. So doing the same thing. So for the second period of motion, it's traveling at a constant speed. So when it's traveling at a constant speed, the big thing we have to realize is the only equation we use for a constant velocity is change in displacement over change in time, right? So since I know it's traveling at 96 radians per second, and I know it's doing so for, it tells me in the problem, 40 seconds, I'm just going to take 96 times 40, and I'm going to figure out the number of radians that I end up getting from this part of the motion. So again, I just multiply by 40, and I get 3,840, and again, radians would be that measurement. So I've got my second stage of the motion. So then for the third stage of the motion, right, again, the stage where I'm slowing down, I just have to use some of the measurements I know from there. Well, I actually already found everything in the previous part, right? In part A, I found all of the information I need. So if I'm using delta theta, I'm just going to use, again, my initial angular velocity of 96. I know from part A that it takes 64 seconds to slow down, and I know it'd be plus 1/2 a negative 1.5 acceleration times, again, 64 seconds squared. So I've got all those measurements to plug in. I just need to plug in and calculate it. So in doing so, when I calculate that, I end up getting 3,072 radians. So that's how many radians I go in the final segment of the motion. So then the total number of radians that I do, right, obviously just the sum of all of those together. So I add up my total number of radians, which again was the 3,072, the 3,840, and then finally the initial amount there, which was just 480. So the total number of radians would be 7,392, but keep in mind this is again in terms of radians. If I want that in revolutions, I need to divide by 2 pi. So the number of revolutions that I end up making is about 1,176 revolutions. Okay, so you say you wanted a revolution, we just got one. But anyway, we actually had 1,176 of them. And anyway, hopefully this question wasn't too bad. Okay, so we're running a little short on question 6 here. So just like Monty Morris in the final seconds of the game, I'm going to try to come in clutch. But I am going to try to get this question done here. So anyway, question 6. They give us a function for the angular velocity, and they ask us what is the angular acceleration at 9.10 seconds, and then how many revolutions has it made after 5 seconds. So the biggest key here is, right, if they give me a function, how do I find the acceleration and the number of revolutions? So for part A, right, for part A, they ask me to find the angular acceleration. The biggest key is the angular acceleration would be the derivative of my velocity function, right? So the acceleration function, again, is the derivative with respect to time of that velocity function. So when I do the derivative, well, my velocity function is 2.00. Again, ignore the radians per second and the snow truck that is outside my house. But anyway, ignoring that, and then minus 2.100 t squared. But anyway, doing the derivative of this, that would go away, and then I would multiply that by 2, so negative 4.2 t to the first power. So negative 4.2 t to the first power is my function for the acceleration. So then at 9.10 seconds, I obviously just have to plug in 9.10. So negative 4.2 times 9.10, and then I calculate it from there. So negative 38.22 radians per second squared. So there's my angular acceleration after 9.10 seconds. How many revolutions has the blade made in the first 5 seconds? The key here is because it is from the first 5 seconds, we're going to assume that our starting position, right, we're going to assume our initial position is 0. Because they're asking us how many revolutions we've made, and that means it wants to know from where we started, how many times did we go around the circle. So we're gonna define then that initial position as 0. The reason it's important for us to do that is because in order to find my function for theta, right, I actually have to integrate my original function. So I have to do the integral of 2 minus 2.10 t to the second. So when I integrate this function, I would get obviously 2t and then minus 0.7 t to the third when I integrate that function, right, dividing by the new power. And then I would have the plus c, but again, because I'm defining the initial position as 0, that plus c ends up being 0. So then all I have to do is plug in 5 seconds, right? So again, plugging in 5 seconds here, and obviously that's easy enough to do. We could use our 5 rule and then our 125 rule over here, but I know you guys can calculate that, so I won't waste your time on it. This ends up being negative 77.5 radians, And since they ask for revolutions, divide that by 2 pi, and we end up getting negative 12.3 revolutions.